Hello, everyone. Welcome back to day 2, all those of you who managed to wake up on time. So let's jump right into it, I guess. I'm going to be doing my final lecture on non-classicality, talking again about non-classicality in Bell scenarios, but I'm going to take a resource-theoretic approach in this talk. So as we saw in the last lecture, when we look at one of these Bell scenarios, we can tell if the common cause is classical or if it's non-classical based on the observed correlations that we see in the experiment. So a natural next question is, can we also tell how non-classical it is? And there's sort of an obvious guess, which would be, okay, we talked about that probability of seeing these particular types of correlations, and we said that's what's bounded by 3/4 in the classical theory. So you might think sort of the more you violate that inequality, the more non-classical the common cause had to be. And that's a good intuition, but it's not actually quite right. There are times when that isn't true. And if you want to sort of understand these things better and why that is, you want a sort of systematic approach to studying these questions. So we need a resource theory. And the resource theory that we're going to introduce to understand non-classicality in these Bell scenarios is called the resource theory of local operations and shared randomness. So sometimes we just call this LOSR, the sort of acronym for these words. So that's going to be the content of today's lecture. And a second motivation for studying this particular resource theory, which is closely connected to just understanding non-classicality in general, but my claim is that if you start reading papers about Bell scenarios and correlations for distributed parties, you're going to run into a huge range of concepts and ideas and results, and it's going to seem like this zoo of just, there's this massive literature, all these ideas people have studied, and they're not usually studied in any sort of comprehensive, unified way. It looks like just this massive, chaotic mess that you have to make sense of, and my claim is that this particular framework will help you understand the majority of those results and ideas. They're all kind of instances of the same kind of resource. So let me start by talking about what types of resources are going to be studied in this resource theory. Sometimes you're studying quantum states, sometimes you're studying quantum channels. In this case, the resources of interest are no signaling quantum channels distributed among more than one party. And I'm going to focus, like in the last talk, on the bipartite case for simplicity. So we have 2 parties, Alice and Bob, and a resource in this resource theory is just some bipartite quantum channel, like this one here. But there's different kinds of resources that have this kind of bipartite channel form, and I'm going to call these different types of resources, where the type of a resource is determined by the nature of its input and output systems. So these systems, they might be quantum systems, or classical systems, or trivial systems. In general, they could also be something else, like GPTs, but here I'm going to focus on these 3 possibilities for the systems in question. And so I'm going to introduce some graphical notation here, where if we have a trivial system, I'm just going to denote that with no wire. A classical system will be a single wire. A quantum system will be a double wire. So that's all consistent with the notation I used in the last talk. But I'm also going to use this dashed double wire to represent an arbitrary and unspecified type. So anytime you see this, it can be any of these 3 possibilities. So that single diagram then represents sort of a whole bunch of different types of processes. And let's consider some special cases of processes. So the most common type that many people study is the just bipartite quantum states. So if you have a process that has trivial inputs and quantum outputs, then in this scenario, that's a bipartite quantum state. Of course, if you have such a thing, you can use it for something. So for example, we talked about what happens if Alice does a measurement on her side and Bob does a measurement on his side. And in fact, we can let Alice and Bob choose among different sets of measurements. And we talked about how if you do that, these kind of sets of measurements on Alice's and Bob's side, then what you end up with is a correlation. And often we call this a black box correlation because we're sort of forgetting about this internal structure and we're just focusing on the input-output systems. So overall, that effective process is like this classical channel with 2 classical inputs and 2 classical outputs. And so sometimes people call these black boxes or just boxes for short, or no signaling boxes. And we talked about how, the particular form for this correlation is this here in quantum theory. And you can read this algebraic expression off just from the diagram, right? You just write down each component of the diagram. So this component here, again, just by virtue of the fact that it has no inputs and it has two quantum outputs, so you know it's a bipartite quantum state. This here is a process that takes a quantum system and transforms it into a classical outcome, so it's a measurement, but it's actually not a single measurement, it's a whole set of measurements. So you can deduce that it must be some collection of positive operators where, if you sum over A, then it's the identity, and that's true for all possible x. So you can kind of, as we sort of saw several examples of in the last lecture, you can kind of start from the diagram, then you just fill in each component of the diagram, and then you compose them using the standard quantum or classical rules. And so this diagram sort of encodes these algebraic equations, and we're going to sort of see that over and over in this talk. Another thing you could do if you started with a bipartite quantum state, well, you could consider what happens if only Alice does a measurement. So now we're imagining Bob does not do a measurement. This is what's called steering in quantum theory. And we know sort of when Alice does her measurement, then the collapse rule in quantum theory tells you that Bob's state will be updated to something new. In particular, if the outcome that Alice sees is A, then upon seeing a particular outcome associated with the measurement operator MA, we're going to steer this initial state to some new state, sigma A, using this formula here, right? We trace the state with the measurement operator on Alice's side, tensor the identity on Bob's side, and that leaves a final state sigma A over here on Bob's side. Of course, Alice can't control which outcome A is observed, so really we end up in this case with a set of states indexed by A, and each state is given by that expression. So this is the kind of steering scenario. Now, normally in quantum steering, we don't talk about just steering to one particular set of states like this. We imagine that actually Alice, again, can choose from among a set of possible measurements. And in that case, we end up with this set of sets of states, right? For a single measurement, we end up with a set of states on Bob's side. When we do a set of measurements, then we'll have a set of sets of states where each of those in the set is sort of the same basic formula, but now there's a dependence on x, the choice of measurement. And this kind of object, which, as you can see, effectively, it's a process that has a quantum output on Bob's side and a classical input and output on Alice's side, just some A given x on Alice's side. So this kind of process is what's known as a steering assemblage. And formally, it's just one of these sets of states. And these things are often named after Einstein, Podolsky, and Rosen. So we talk about the EPR steering scenario because they were the first people to study this kind of process. So let's go through an example of steering. So imagine you start with this state here. This is the singlet state. And now Alice can choose among three different measurements in three different bases. The first basis measurement we'll consider is the 0-1 basis. Well, you can see that if she gets the 0 outcome, then the state on Bob's side will be updated to the 1 state. If she gets the 1 outcome, then the state of Bob's system will be updated to the 0 state. But if Alice measures in a different basis, like the plus-minus basis, then as Rob talked about, you can rewrite this state also as plus minus 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 plus. So in this case, if Alice gets the plus outcome, then Bob's state will be updated to the state minus. If Alice gets the minus outcome, then Bob's state will be updated to the state plus. So you can just check that with a quick calculation. Similarly, if Alice measures in the plus I minus I basis, then the updated state on Bob's side will be either minus I or plus I. So in this case, then, the steering assemblage that you get will be a set of sets of states, one set for each measurement. So the first set is for the first measurement, and it just contains two states, the 1 state and the 0 state. And these are now subnormalized states because neither of these states occurs with probability 1. In fact, they both occur with equal probability. So sometimes people talk about assemblages as sets of ensembles. So you could kind of separate out this probability and the state, but it's easier just to think about the subnormalized state because this contains both the information about what the updated state will be and the information about the probability with which that state will be the one that Bob is left with. So this is the set for the first measurement, then we have the set of states for the second measurement, and the set of states for the third measurement. And this whole collection is called the assemblage. And the reason Einstein and Podolsky and Rosen were interested in this question is that if you think the quantum state is a state of reality, if you think that it's ontic, then this is already a proof of non-locality, as Rob sort of mentioned. So if these are 6 different possible ways that the quantum system on Bob's side can be, well, Alice, she can't choose exactly which of these 6 Bob's state will end up in, but she can choose whether Bob's state will end up as one of these 2, or one of these 2, or one of these 2, because she can choose which of these sets she steers to by her choice of measurement. So Alice can choose which state of reality, or which of these states of reality Bob's system will end up in. And so if you think, as I said, if you think the quantum state is a state of reality, then Alice can make this happen no matter how far apart Alice and Bob are, because if we look at this causal structure, Bob could be very far away, and this is just some pre-established entangled state. So that bothered Einstein. He said, obviously, we shouldn't have this kind of spooky action at a distance. So that suggested to him a more sensible conclusion, which is that the quantum state is just a state of knowledge. These are not physical descriptions of the state of reality in Bob's lab. They're just descriptions of what Alice knows about what's in Bob's lab. And from that perspective, it makes a lot of sense that you would update your state of knowledge when you learn information by doing a measurement, which is exactly what Alice is doing. So that's kind of the conceptual reasons why people study quantum steering. Formally, the mathematical object they study are these sets of states called steering assemblages. Another thing you could do, if I give you a bipartite state, is you could bring in some extra system on Alice's side and some extra system on Bob's side, and you could do some correlated measurement of the 2 systems in Alice's lab, and Bob could do a correlated measurement on his 2 systems in his lab, and they each end up with some classical outcomes. Once again, if you just write out the explicit form for each of these processes, this is what an object of this sort looks like. For our purposes, though, let's just focus on the overall shape of this process. It's a process that has 2 quantum inputs and 2 classical outputs, one on each side. So on each party, we have sort of a measurement-like process, right? It takes in a quantum system and spits out a classical outcome. So I'll call this a distributed measurement. In particular, if Alice and Bob want to do some kind of joint measurement, like a measurement in some entangled basis of states, this is one way of doing that. Normally, if you wanted to do a measurement in some entangled basis, you might bring the 2 systems together, make them interact, and then do a measurement. Here, we never interact the 2 systems, we just use some prior shared entanglement, and my claim is that you can use this shared entanglement to do an entangled measurement on these 2 systems. So that's sort of one example of why you might care about these kinds of distributed measurements and how you can use entanglement to build new kinds of distributed measurements that might be useful to you. Yet another thing you might do with an entangled state is you might do the teleportation protocol. So you bring in the system that you want to teleport, you do some entangled basis measurement on half of an entangled state with the system to be teleported, you get some classical outcome, you send that over to Bob, who does a correction operation on his half of the entangled state. That's the teleportation protocol. If you choose this measurement and this correction operation carefully, then the overall effective channel from this input to this output is the identity channel. That's the point of teleportation. And now here you might say, okay, this doesn't quite fit the pattern so far because we have now communication between Alice and Bob. All the other examples we were giving imagined Alice and Bob are far apart and not communicating. So this doesn't immediately sort of fit the mold, but it turns out if you look at this process prior to the communication, so if you just forget about that last step of teleportation and you just focus on processes of this shape, it turns out that actually that has all the relevant information that you need for figuring out if teleportation is possible or not. So this kind of process has also been studied in the literature. People call them quantum teleportages. And we can see the type of process here. It has a quantum input on Alice's side and a quantum output on Bob's side. That's like the thing you're trying to teleport from and to. And there's some classical outcome on Alice's side. So that's the sort of type of process. So all of these are resources that we're going to study within this resource theory. It covers this like broad range of scenarios and types of things you might be trying to do. And in fact, there's a whole bunch more, and I'm not going to go through all of them. But the point is, all 10 of these types of processes have been studied in the literature, many of them sort of in hundreds and hundreds of papers. Some of them are a little bit more new, but all of them are sort of motivated by particular foundational questions or practical questions of interest. And in fact, that's not even comprehensive. There's even more scenarios, which, as far as I'm aware, people have not yet written papers about these particular types of processes. So there's kind of an open question here, like, is there some foundational or practical significance to these? Probably there is, if you think about them in the right way. At a minimum, each of these will give you a possibility of some new manifestation of non-classicality. And you'll see what I mean by that as we go along. There's still more types, which I haven't listed, because the remaining types, other than the 15 that I showed so far, are all trivial. Again, in a sense that I'm going to make formal. So if you have, for example, a process of this type, this is just a classical shared probability distribution, and that's kind of useless. In the resource theory we're going to define. Some of the processes are purely local, so here Alice isn't doing anything. It's all on Bob's side. So again, that's going to kind of be trivial in the resource theory we're talking about, and so on for the remaining types. But the point is, there's this wide variety of types, and we're going to study them all simultaneously. So now let's get into the actual resource theory. So which of these resources, if I give you one of these processes, right? We have all these different kinds of things that we might want to study, sets of states, sets of states, distributed measurements, all these types of things. If I give you one as an example, how can you figure out if it's useful or not? What does that mean? Well, the key step in any resource theory is to identify the relevant set of free operations. Everything else, the entire structure of the theory, all the monotones, the measures of resourcefulness, the asymptotic conversion conditions, all of those things follow just from the free operations. So this is the key step. And so let's ask ourselves, what are we trying to do here? What are we trying to achieve? And what are the physical restrictions in the scenario that we're studying? Well, we're in this kind of Bell scenario where we have these two distant parties. So we're imagining that they have no cause-effect relationships between them. They have no ability to communicate to each other or causally influence one another. But we're imagining that locally they can do whatever they want within their laboratory, within quantum theory. And we're also allowing that they have some prior established common causes. But we want to study non-classicality of common cause. That's the kind of resource that's powering a Bell inequality violation or anything that we want to do here. So we're going to choose to allow the local stuff to be free. So anything local quantum operations are all free. And we're only going to allow the classical common causes. In that case, anything that's non-free, any valuable resource, will be a resource of non-classical common cause. So that motivates these free operations, local quantum operations, and classical common causes. Another word for a classical common cause is shared randomness. It's just like flipping a coin and sharing the values of that coin with both parties. People usually refer to classical common causes as shared randomness, so we're going to call this the LOSR resource theory. These are the free operations, and whenever you have something that's not free, again, then you know that it wasn't just some classical common cause, it was some non-classical common cause in the process. So what do the free resources look like in this theory? Well, they're the ones that can be simulated, again, by local operations and shared randomness. Diagrammatically, local operations are just these local channels that Alice and Bob can do, and shared randomness is just this shared bipartite classical state. So again, it's just a joint probability distribution over two classical variables, one which Alice has, one which Bob has. So now let's focus on the special case of what does a free bipartite density operator look like? Well, it's LOSR free if it decomposes in the following way. So on Alice's side, we need to have a quantum channel which has no input and it has a quantum output. On Bob's side, similarly. So this is just a product state, right? It's a state on Alice's side and a state on Bob's side. So like some rho tensor sigma. But then we also can have our shared randomness, which we can use to correlate our choice of local preparations. So algebraically, you just sum over some probability distribution which of these states you choose. So we have these correlated product states. And this should look familiar. This is just the standard form for a separable state of a bipartite system. Any state which does not decompose in this way is a non-free resource and is entangled because it's not separable. So we see that by thinking about these LOSR free operations, we've recovered the fact that the useless states are the separable ones and the useful states, the non-classical states, are the entangled states. So we kind of get what we expected to come out. What happens if we do this for correlations, these black box correlations? Well, once again, it's LOSR-free if it decomposes as local operations, which the appropriate typed local operations now have classical inputs and outputs for both sides. And again, we can correlate our local operations with our shared randomness. So this is the most general form of such a correlation that can be LOSR-free. And if we now just write out the algebraic expression for these three components and we put them together, well, we did that in the last lecture, right? It's just this factorization condition. And so again, this looks familiar. This is exactly those correlations that satisfy the Bell inequalities. So often people just call these the local correlations. If it doesn't have this factorization form, then it's a non-free resource, and we say often that it's just a non-local box. So once again, we've recovered the obvious sets from our resource theoretic approach. But we can go further. Let's now look at bipartite steering assemblages and ask which ones of those are LOSR-free. So hopefully you're seeing the pattern by now. Locally, we imagine the free stuff that has the appropriate types. So on Alice's side, it's classical to classical. On Bob's side, it's trivial to quantum. Then we put in our shared randomness. We write out the algebraic equation that is represented by this diagram. And you have this. You have on Alice's side, you have this conditional probability distribution, P of A given X and lambda, as we saw before. On Bob's side, you just have a quantum state preparation, which is dependent on this shared randomness. And then we average over this P of lambda. As always, we correlate these two processes here and here with the shared randomness. So this is the form for an LOSR-free steering assemblage. If all of the states in those sets of quantum states can be decomposed in this form, then the assemblage is free in this resource theory. And if you look at the literature, even before people had this LOSR resource theory, they had already been studying steering for some number of years, and they'd identified that exactly the ones of this form are the ones that are kind of uninteresting, not useful, and the term that they introduced for that is unsteerable. And so we see here that, once again, we reproduce the divide between what was considered interesting and not interesting within this sort of same methodology. If your assemblage does not decompose in this form, then it's a non-free resource, and we say that it's steerable. So here are the examples we've seen so far. As you can guess, this pattern repeats. So if you go to teleportation, once again, you write down this kind of decomposition in this free sense with the appropriate types. This exactly reproduces the divide between what people had called sort of uninteresting and interesting processes for teleportation. And you go through all 10 of those different types of processes that I introduced, and you find that totally independently, every single one of them reproduces exactly this LOSR condition. So here we've sort of identified the fundamental unifying feature of all of these different types of resources and all 10 of those different scenarios people had studied. You can understand them all just as instances of free or non-free resources in this single resource theory. But now we want to go more, we want to say more than just which resources are free or non-free. We want to say which resources are which ones are super valuable, which ones are more valuable than others. We want to introduce some quantifiers of how resourceful a resource is. And to do that, as Rob talked about, we need to introduce transformations, because we say that one resource is more resourceful than another if and only if it can be transformed into the second resource. So what do transformations look like? Well, we can let the diagrams do a lot of the work for us. So if you start with a bipartite state and you want to convert it to another bipartite state, in this resource theory, the most general thing you can do, well, locally, you can do whatever you want. We're trying to transform a state into a state, so the natural thing to do is a quantum channel on each side, and as always, you can correlate your local operations with your shared randomness. So this is the most general transformation from a state to a state. You see that after all this procedure, you're just left with another bipartite state. If you start with a box, this black box correlation, and you want to convert it to another black box correlation, well, now, of course, you can post-process your outcomes. You can pre-process your inputs. In fact, you can locally keep track of your pre- and post-processings and correlate them with this side channel, because that's all sort of local to Alice's lab. Bob can do all those same things. And then we can correlate our choices of pre- and post-processings with our shared randomness. So this is the most general thing you can do that transforms an initial box, here in black, to this effective overall box. What about transforming a quantum state into a correlation? Well, the thing that we've seen in the Bell scenarios, if you want to generate some black box correlation, you take your quantum state and you do local measurements on it. But in this resource theory, that's not the most general thing you can do, right? You can do more than just local operations. You can correlate your local operations with shared randomness. So now this is the most general way of transforming a quantum state into a black box correlation within this resource theory. So that's the most general free operation. And again, hopefully you're starting to see the pattern here. So you can always sort of just draw this figure where all of these types are arbitrary, and then specialize your system types of the given resource here in the middle, and the target resource here at the output. So for example, if I want to figure out the most general LOSR transformation from a channel to an assemblage, that might sound hard if you weren't thinking diagrammatically. If you were thinking algebraically, you'd really have to like puzzle over that, and you could work it out eventually. But with the diagram, it's basically trivial. Since you're starting with a channel, you know that all 4 of these processes are quantum. Since you want to turn into an assemblage, you know that Alice has a classical input and a classical output, and Bob has a quantum output. And so you can just kind of repeat this sort of general procedure to figure out what the most general transformations are. And again, once you have the diagram, then you could convert that easily into the algebraic expression just by plugging in the individual components and then composing things. So once we have once we know what the most general transformations are, we can now start asking which resources can be transformed into which others. And when we do that, we can start to build up this pre-order of resources that Rob talked about. And now this is going to be a very large, complicated pre-order, right? Because Rob was talking about pre-orders over a single kind of object like quantum states. But here we have a pre-order over all these different kinds of processes. So let's do some examples, like maybe we have a singlet state, we have the Cyrilson box, that was the correlation that we said violated the CHSH inequality as maximally as possible within quantum theory. So that's a particular kind of correlation. We could build a particular kind of distributed measurement where you take your singlet state and you do these local Bell measurements on it. So this is in fact an example of generating a entangled measurement on these 2 inputs using the singlet state. We could build an assemblage where we start with the singlet and we measure in X, Y, and Z. That's the assemblage we saw earlier as our explicit example. We could build another kind of assemblage where we do the same thing, but we only measure in the X and Z bases. So it's a slightly different assemblage. And you could take a million different resources of 15 different types, and you could start asking which of these can be converted into which others, and consequently, which of these is more resourceful than which of the others. And you can work it out for these 5 examples, and in fact, most of these are pretty obvious. So the singlet obviously can be transformed into any of these these 3 resources, right? Because you can see that manifestly by construction, all 3 of these are just the singlet with some local operations on it. So the singlet can be transformed into those 3. It can also be transformed into the Cyrilson box, because you might remember the optimal quantum strategy. One of the optimal quantum strategies is just to take this maximally entangled state, like the singlet, and then do some appropriate measurements on it. What is less clear is that if you give me this distributed measurement, this kind of ability to do a joint entangled measurement on Alice and Bob, you can convert that back into the singlet. That, to me at least, isn't obvious at all. I'm going to prove it to you later in the lecture. But for right now, it shouldn't be at all clear that you can turn a bipartite distributed measurement into a perfectly entangled state. But we'll see that we can. And once you realize that that's possible, well, then it follows that that thing can also be turned into these other 3 processes just by transitivity. And you can turn this assemblage into this assemblage just by sort of choosing to never use the Y measurement that you had access to. And you can turn both of these assemblages into the Cyrilson box just by doing the appropriate local measurements on Bob's side. So this, I claim, is sort of the set of possible conversions. So we see now that these top 2 resources are more resourceful than all these other 3, strictly more resourceful, because none of these 3 can be converted back into either of those 2. So then it stands to reason there will be some monotone we can introduce that can discriminate which of these are more and less valuable. And it turns out you can define some absolute robustness monotone, which takes these particular values. So you can see it's highest on these top 2 resources, it's got a lower value on this assemblage and an even lower value on these bottom two resources. So you see then that this, for example, this correlation, even though it's very non-classical as a correlation, it's a lot less valuable than a singlet state, for example. So it can't be converted freely into that singlet state. And yeah, this is obviously just a tiny slice of what is this ultimately very large, rich resource theory. Okay, any questions so far? All right, so the next topic I'll cover is we can study lots of other interesting questions aside from this pre-order. So we can ask questions like, are there ever any transformations from one type of resource to another type of resource that necessarily destroys all the non-classicality? So if this happens, it would tell you, don't even bother looking for these kinds of transformations. They're just always going to throw away all the interesting non-classicality. So I'll call these non-classicality degrading type changes. And my claim is that one such example is if you start with a black box correlation, even one that's very non-classical, and you try to transform it into a bipartite entangled state, that entangled state will always be free. It'll always be separable. And the proof of this, again with diagrams, it's really easy to see. So what's the most general transformation from a bipartite correlation to a bipartite state? Well, we just take the appropriate local pre and post processings and we correlate them with our shared randomness. So this overall process, as you can see, is a bipartite quantum state. And now, all that we have to recognize is that without loss of generality, we can take these side channels on Alice's and Bob's side to be classical wires. So in general, Alice and Bob can have quantum systems locally that they use to correlate their pre and post processing. But because these pre and post processings are on classical systems, there's no extra generality in having quantum systems on the side. And the way to see that is just note that inside each of these boxes here, ultimately somewhere inside this box, you have to prepare the quantum state that you're going to send along the side channel. So wherever that quantum state is prepared, you can just drag it up and consider it part of this post-processing instead of part of the pre-processing. And that quantum state, of course, can be correlated based on this classical variable, so that's why we now have a classical wire here instead of a quantum wire. So it's just a sort of diagrammatic rewriting of this diagram, and it ultimately ends up in this side channel being classical rather than quantum. And if you do that on both sides, then you show that this is the most general conversion from a box to a quantum state. And now we're basically done, because if we focus here on the process up to this point, so in the shaded region, you see that this process, it has no inputs and it has classical outputs on both sides. So that's just a joint probability distribution over these classical variables and those classical variables. And Alice and Bob already had access to arbitrary, free, shared randomness. So this whole thing is no more general than the thing they had at the very start, just some shared classical common causes. So if this whole thing in gray is free, and then we do some local operations on a free thing, that's also going to be free because local operations are free. So it follows that this whole thing is free, and we didn't lose any generality in that argument, so that shows that the bipartite state you're left with will always be separable in any such transformation. And in fact, if we look at other types of transformations, like transforming boxes into assemblages, by a similar kind of diagrammatic proof, you can see that you'll Okay. Sounds like it's working, at least within the room. Okay. Right. So as I was saying, the overall procedure here is just the teleportation of this system to this system, which means it's an effective identity channel from here to here, which means that this whole thing is just equal to E itself. So if you start with E, this is a local operation you can do to transform it to an object of that type, and then the thing in red here is something you can do to transform that procedure all the way back into E. So and these are all local operations. They're all on Alice's side. So these are all free operations. So we've established then that for any channel, we can transform it into an object of that type and then back. And that's the proof that you haven't lost any non-classicality, even though you've ended up with something that just has classical outcomes. And of course, if other parties, like Bob, had a quantum output, you'd do the same thing on Bob's side. And at the end of it, all the different parties would have only classical outputs. But if they ever wanted, they could get back to where they started. And that is also the proof that we saw from earlier, that if you had that particular distributed measurement, then you could convert it back into the singlet state. Yeah, question?
So the sentence you're writing here, that every resource can be converted to one classical output without regretting non-classicality?
Sorry, I couldn't quite hear.
The sentence that is written just over the box, it means that there are some resources that can be converted to classical resources and then back to non-classical resources.
Not to classical resources. So this object has only classical outputs, but it's not a classical resource. It's still non-free in the resource theory.
Since you say every resources plus works for the resources we taught on the slide before.
Well, so the claim is without degrading its LOSR non-classicality, if you started with something that had no non-classicality to start with, it wouldn't be degraded, but it would still be zero. So it doesn't, this process doesn't add any non-classicality or remove any. It's in the same equivalence class as the starting resource. So if the channel E here was free to begin with, then this overall process will also be free. Thanks. Okay. A sort of analogous question. You might hope to do this with other types. So you might ask, okay, what about when we transform into box type correlations? So for example, you could ask, do all non-free states, so do all entangled states, can all entangled states be transformed into some correlation that is non-free? It turns out this answer is kind of famously no. So Werner proved that there's some entangled states that don't violate any Bell inequalities. So this is sort of just in contrast to the result on this slide, where you could always do a transformation to get something non-free in the new type. Here's something where, in general, when you do the transformation, some of the states will go to non-free boxes, but other states will not be able to go to non-free boxes. And this is the more generic case. If you give me two random types, typically some of the non-free stuff can be transformed into some of the other non-free stuff, but some of the non-free stuff cannot be transformed into anything valuable. So as you sort of change the type of a resource, there's this kind of delicate interplay between the types of non-classicality that stick around or don't stick around. Okay. Now something some of you might be wondering is, I've here been talking about entanglement as a property of this LOSR resource theory. But Rob was talking about entanglement as a property of the LOCC resource theory, with local operations in classical communication. And this is the one that's much more famous because it was invented like 20 years before the LOSR version. So what's the relationship between these topics? Well, if we go all the way back to Schrödinger, he said that a pure state is entangled if it's not a tensor product of two components. And then this was generalized later to mixed states. So we say that a mixed state is entangled if it's not separable, a mixture of product states. And then, over the years, entanglement was realized that it was realized that entanglement is useful as a resource for quantum communication tasks, like teleportation and quantum Shannon theory. And so in this context, where people were first using entanglement to study quantum communication, they were kind of interested in what can you do, what kinds of non-classical communication can you do? And so it was natural for them to ask, let's take the free operations to be classical communication, then anything which is non-free has to be a resource of non-classical communication. So if what you're studying, if the kind of physics you're interested in is communication tasks, then it's natural to allow classical communication for free, as well as the local operations. And so for this reason, because entanglement was first studied in this context of kind of communication tasks, that's why LOCC was the thing that was proposed at the time. And so the way that people started to think about entanglement is that one state is at least as entangled as another, if and only if it can be converted to the other using LOCC operations. This is just the standard definition of more resourceful in a given resource theory, but relative to this particular LOCC choice. And in this talk, I've been proposing that we use the same definition, but we use the LOSR operations. And qualitatively, both of these resource theories have the same divide. They both pick out the entangled states as valuable and the separable states as free. So they agree on the basic qualitative definition, but quantitatively, the pre-orders are very different. And so the quantitative notion, like the measures and monotones of entanglement in these two different theories, are very different. So we need to ask which of them is more appropriate. The answer, as I've sort of hinted at, it depends on the situation. So in the case of our interest here, where we have a common cause scenario, like the Bell scenario, my claim was we're trying to study non-classicality of this common cause in the scenario. So for that reason, we take the classical common causes to be free, and we don't allow any communication because these parties are far apart, and we use the LOSR resource theory. But as I said a few slides ago, in any sort of cause-effect or communication-like scenario, it will make sense to allow the classical communication for free. Now the non-free resources are resources of non-classical communication rather than non-classical common causes. So it kind of depends what kind of processes you're studying, which resource theory is going to be the most insightful. Now that said, it wasn't realized until fairly recently that this LOSR approach should be used over in this Bell context. So people had been using the LOCC approach in this context as well, and that led to a lot of confusions. And so I'm going to introduce one of those confusions, and then I'm going to show how you can resolve that confusion by thinking in this LOSR approach. So these confusions actually had a name. They were so popular, there were so many papers written on this topic that people started to call them the anomalies of non-locality. So these are just a bunch of examples of papers where each of these papers proved one of these anomalies, where what we mean by the anomaly is that sometimes having strictly more entanglement means strictly less ability to generate non-locality. And that sounds kind of crazy. If you have more non-classicality, more entanglement, why would that literally prevent you from generating some non-classical correlations? To put it a bit more formally, these papers showed that there exist measures of non-locality which can be maximized by a partially entangled state, but cannot be maximized by a maximally entangled state. And so I'll give you 4 examples. Consider the family of pure entangled states on a pair of qubits. So you can always write that as some cosine theta 0, 0 plus sine theta 1, 1. So this is sort of the representatives of all the equivalence classes of any 2-qubit pure state. And as theta ranges from 0 to pi over 4, we're ranging from the product states over to the maximally entangled states at pi over 4. And in the LOCC resource theory, there's a single monotone. This is a total order of states, so that there's no incomparable resources. For each point on this line, you have strictly more LOCC entanglement as you go further and further to the right, as theta increases. And again, naively, having more entanglement, being further to the right on this line, can't hurt you for generating non-locality. But what people found is that actually, if you try to use these states to run a Hardy proof of non-locality, that's one particular kind of correlation you can try to generate, which Ela is going to talk about more in her lectures. Or if you try to use them to violate a particular kind of Bell inequality called a tilted Bell inequality, or if you try to use it for something practical, like extracting some secret key in some key distribution scenario, or if you look at the distance from the local set, which is another kind of measure. So all 4 of these are sort of ways of measuring how non-local your correlations are. And for all 4 of these, and a bunch of other examples in those papers that I'm not going to talk about here, it was found that the optimal state is not the maximally entangled state. It's some state in between here. And moreover, it's a different state for each of these 4 different possibilities. So it just seems like there's no connection between non-locality and entanglement. And people were very surprised by this. They called it the anomalies of non-locality. And as I mentioned, there was a lot of sort of discussion and argument, how should we understand this? And we can kind of make it look even more problematic, like we can see why this is confusing if we think about it in this kind of resource theoretic way. So entanglement theory says the reason we call phi plus the maximally entangled state is because it can be converted freely into any other entangled state. In particular, there's something called a Hardy state, which is just a partially entangled state. So a maximally entangled state can be freely transformed into it. By definition, this Hardy state is the one that generates the Hardy correlation, which is the correlation that maximally violates this, that has the highest probability of running one of these proofs of non-locality. So this Hardy state can generate that particularly interesting correlation, but what entanglement theory also says is that this maximally entangled state cannot be used to generate the Hardy state. That's what Hardy showed in his first paper. So you have these 3 kind of conditions that people had independently derived, and there seems to be an inconsistency here, right? If you can turn the phi plus state into the Hardy state, and the Hardy state can generate this correlation you want, then how can it be that you can't turn your maximally entangled state into that correlation? So it just doesn't make sense to use this word of maximal entanglement if there's something you can do with the Hardy state that you can't do with the maximally entangled state, then in what sense is this a maximally resourceful state? It just isn't. But the reason this is an apparent inconsistency is because people derive this conversion relation with LOCC as their notion of entanglement, and they derive these conversion relations by imagining local measurements in a Bell scenario. So these are just local operations. So they're using 2 different resource theories to compute these 3 conversions. And I argued in this talk that all 3 of these things should have been evaluated relative to LOSR. So all 3 of these were just inappropriate choices of the relevant set of free operations for the scenario in question, which is these distributed parties. And if you use LOSR operations, then one of these conversion relations changes. Namely, it's no longer the case that the phi plus state can be converted into the Hardy state. The other 2 operations or transformations don't change. It's still possible to go from here to here, and not possible to go from here to here. But now these 3 sets of transformations are consistent. So the thing that has changed is that in the LOSR approach, these 2 states, the phi plus state and the Hardy state, are incomparable. The phi plus state is more entangled than the Hardy state according to some measures, but the Hardy state is more entangled than the phi plus state according to other measures. So you have to change your intuition about what is the maximally entangled state of a pair of qubits. There's no longer a single maximally entangled state. And hence these terms, I'm going to no longer refer to this phi plus state as a maximally entangled state, and I'm no longer going to refer to that as a partially entangled state. Those terms came from LOCC entanglement theory, and they're just not appropriate here any longer. And in fact, if we consider that family of states from before, which we said there was a sort of single monotone, it's a total order in the LOCC approach, all of those states, every point on that line is incomparable with every other point on that line, except of course the free point here, which is less resourceful than all the others. So in the LOSR approach, even for just states on a pair of qubits, you have this really complicated preorder. Well, it's simple in the sense that every point in the preorder is unordered with every other point. They're all maximally entangled states. So it follows then that there are multiple monotones in this resource theory. Some of those monotones will just agree with the LOCC monotones, but there will also be monotones running the other way. So where you get more non-locality as you move further to the left. And in fact, for each of those anomalies that people identified, like generating a Hardy paradox or generating a secret key, each of those had its own optimal state and defines a monotone which is peaked at that optimal state. So you see that according to some monotones, this particular theta optimal is the maximally resourceful state. And that's exactly why it's the most useful for certain tasks, like extracting a secret key. Now, you might also think this resource theory is kind of, it doesn't have a lot of structure since all of these points are unordered. But of course, if you go beyond just a pair of qubits, then there will be a lot more structure and there will be plenty of ordered resources to study. But here in the simple context, you just can't convert any of these states into each other under the free operations. So the standard conclusion that people drew in the literature before the LOSR approach was introduced is that non-locality and entanglement are just somehow different. You thought that entanglement was useful for non-locality, but it's not always true. But that's really not the best conclusion you can draw. The better conclusion is that non-locality and LOCC entanglement are different resources. They're not closely connected. But once you study LOSR entanglement, they are closely connected. They're manifestations of the same resource. They all fit into the same resource theoretic approach that we talked about today, because they're all manifestations of non-classical common cause processes. And in a slogan, more non-classicality is always better if you're measuring it correctly. And that's all I have time for. Once again, I recommend these references. There's some talks here on PIRSA and some papers that cover what I talked about. Thanks very much.
I was wondering how it can be used in practice now, this LOSR entanglement. I mean, okay, it can be used in practice, but since you don't really have a measure, I mean, it seems to be very unordered. So is it not a bit disappointing that it's so hard to judge which states are more non-classical than others?
I would say no, it's the exact opposite of what you just said. It's not that there are no measures, it's that there are many more measures. So in fact, every single LOCC measure is formally a monotone in the LOSR theory, but there's more monotones in the LOSR theory. And it's those new monotones that give you strictly more information than the LOCC approach. So that's why, for example, in this resource theory, there will be a monotone that tells you precisely how useful a state is for extracting a secret key. In the LOCC approach, it just seemed there was no connection between extracting a secret key and entanglement. In this approach, I can give you the exact monotone. I mean, here I'm just kind of sketching it very vaguely, but you could compute the exact function that tells you how useful a state is for that task. And similarly, for any of these other tasks, you can find the exact LOSR monotone. So it's a strictly bigger set of monotones, and consequently, you can kind of get more information than in the LOCC approach. And consequently, I mean, here was kind of an explicit example where we saw that people were getting confused because they didn't have access to those new monotones. There's probably still other scenarios, like LOCC entanglement theory is now being used in condensed matter, astrophysics, like all across physics, which has nothing to do with communication scenarios. And there's no reason to think that those are the right monotones. Luckily, they're not problematic, at least if your choice is between these two resource theories. As I mentioned, every LOCC monotone is also an LOSR monotone. Now, I'm not really claiming that LOSR is the right approach either for cosmology or condensed matter. I don't really know what the right notion of entanglement is, but you have to realize that it's sort of dependent on the context, and it's unlikely to be the LOCC approach, which is sort of just assumed by default because it was the first one that was invented. Yeah.
Thanks. I have a question on the proof for the transformation that preserves the resource. I mean, you are using an untangled state to go back to get a state by doing a Bell measurement. And why do you have the right of of taking a maximally entangled state in this resource theory? It costs nothing.
You're asking about this?
Yes.
Okay, sorry. Can you say the question again?
You use a maximally entangled state. I mean, just to prove that it's equivalent.
Yeah.
Why in this context it costs nothing of using this maximally entangled state? I mean, you can just say, okay, I have the right of using this maximally entangled state.
Right. So you're saying, like, how is this a free operation if
Yes.
it's a maximally entangled state? The answer is this is a maximally entangled state completely within Alice's laboratory. So we're kind of studying non-classicality across this divide between Alice and Bob. So if Alice and Bob are far apart, then it might be hard to get an entangled state shared between them. Whereas within Alice's laboratory, she might be able to build as many local copies of entangled states as she wants. Now, of course, that's also an idealization. Resource theories always come with some idealization because nothing is ever truly free, right? It still takes some effort to build a local maximally entangled state. But, you know, it's a pretty good approximation. We have the ability to prepare these sorts of things.
Okay.
Thank you for the fascinating talk. My question is, I think, specific, but in the slide where you show the apparent inconsistency, I was wondering if we can consider local oscillator as just like the subset of LOCC, so that we can think the whole discussion you did on that slide close.
So I think I understood your question. Tell me if I got it wrong, but so you're saying on this slide, what if we took all three of these to be under LOCC?
Yeah, or the opposite.
Yeah. Or
like,
LO? Or,
yeah, because
right.
I thought, one of them is the subset of the other, I thought,
Right, so
naively.
if you evaluate all three of these conversions relative to any single well-defined resource theory, then of course it'll all be consistent. So if you allow this to be LOCC and this to be LOCC, then what happens is you can also transform, like this becomes possible and this becomes possible. And that's obviously true, because if you have classical communication, you can generate any correlation. You can just send the classical values you want Bob to have over to him. So that's another way to retain consistency, but in a sort of trivial way that doesn't really teach you anything. It just says, under LOCC, you can generate every possible correlation between the parties.
Okay, I understand.
And
Thank you.
similarly, if you pick just LO, then this would no longer be possible, and this would no longer be possible. So it would all be consistent again, because you just can't do very much under local operations alone.
Okay, so making it consistent is not the main part of your discussion, or like not
That's
the
right. That's
main
right. It's not
direction.
just about consistency.
Okay, sorry. Okay,
But that's a good point as well, though. Like yeah.
thank you very much.
Oh, sorry. Going back to when you talked about EPR steering, because you said that like it was a good argument that, for example, Einstein concluded that the state was epistemic, like we should understand it as being like our state of knowledge. But then I would like ask you, how do people who are like argue that the state is ontic, like how do they take the EPR steering argument?
Yeah, well, prior to Bell's theorem, I think a sort of honest and well-informed physicist would have said, yeah, I think you've got a pretty good argument there that the quantum state is epistemic, because otherwise I have to accept this ridiculous conclusion of non-locality. Yep. These days, people usually would say, unfortunately, Bell's theorem tells us that you have to have non-locality, and therefore, even though this is non-locality, in some sense you could say this is like more non-locality than is needed. You're not forced to conclude non-locality from EPR, but you are forced to conclude, according to some people, non-locality from Bell scenario. So then they kind of work backwards and they say, okay, so everywhere else that you see non-locality, you shouldn't be surprised because quantum theory is non-local. I don't like that approach. I think it's still true that you can kind of look at many different phenomena in quantum theory, and you can say, you know, think of it like being a detective, right? Like, is the quantum state you look at 100 different experiments and you ask, in which of these experiments is the quantum state behaving more like a state of reality, and in which is it behaving more like a state of knowledge? And on that entire long list of phenomena that the toy theory reproduces, you see that the quantum state is behaving like a state of knowledge. And so, to me, I think you shouldn't just pick like the worst case scenario, the Bell non-locality, and throw out all the other evidence. So maybe that answers the question.
Yeah.
Roughly.
Okay. Thank you.
Maybe a last question, and then where's the microphone?
So we talked about kind of how to compare resources with respect to the orderings you define, but we didn't talk about the types of orderings. Like, do people know what those types are, or whether the orderings are, where are they dense, for example, things like that.
Can you clarify the question?
There are types of orderings, like I can ask whether the resources are ordered, like, is it a good ordering, right? Or
What is
whether
it?
between any two resources there is another
Uh-huh.
with respect to your ordering, like questions
Right.
that are
I see. So just more of the detailed properties of the pre-order.
Yeah.
Have those questions been studied? At least in the context of some special cases. So what I would say largely is that, as I sort of mentioned, the pre-order for all resource types is this very large, very complicated thing, which I would say not that much has been studied about as of yet. But if you look at specific cases, so if rather than looking at kind of all different types and the pre-order over all types, if you just look at the pre-order over boxes, for example, then we've studied some of those properties, and we've proved the height of the pre-order, the width of the pre-order, other properties of that sort. I think for quantum states, we've done a little bit of that work as well. So usually people study this, kind of break the problem down into smaller cases. You pick a particular type and study that. Even then, though, most of the types, I would say we don't know very much about the pre-order, and there's just a lot of questions to be answered.
Then do people think about introducing ordinals to the story, or is that like out of the question? No reason to do that.
I'm not sure.
Like to quantify the chains, the largest chains you can arrange.
Yeah, I think that's
okay.
definitely an interesting question. This resource theory hasn't been around that long, so largely it's just because no one has gotten around to it yet, but those questions need to be answered.
Thank you.